All right. So welcome back, everyone. So we're going to start off our research spotlight session. So I'm here with a few members from our Faculty of Applied Science who are going to share with you some of the amazing research that they're doing and just some of the ways that engineers are making an impact in the world. So this research is often actually multidisciplinary, interdisciplinary rather, meaning that people from different engineering programs or faculties like science and medicine all work together. So hopefully these short introductions to just some of the research happening at our faculty will give you a better insight into the variety of topics a degree in engineering may allow you to explore. So engineering research and the application of this research is truly changing our world for the better. So with that, I will invite our first research spotlight to the stage. And Emily, of course, is already here with me here. So I'd like to introduce to you Emily Me. Emily is a hydrogeological engineer with a Bachelor of Applied Science and Master's of Applied Science in Geological Engineering from UBC Vancouver. Emily specializes in groundwater, so hydrogeology, to tackle contamination and water supply problems and design systems that protect people and the environment. Her master's research was inspired by industry projects that collect large volumes of groundwater data, but still struggle to understand complex groundwater systems. Emily's presentation today will focus on exploring complex groundwater data with machine learning. So Emily, welcome. Thanks for joining us here today. Before we begin, can you share why you decided to pursue a career in engineering and why did you choose your field of study?
Yeah, I actually didn't choose engineering. Out of high school, I had a really difficult time deciding what I wanted to study. And I decided to go to UBC for geological sciences to specialize in groundwater. And I chose that path basically because I kind of been interested in environmental issues and social issues. And I thought groundwater was a field that really brought those two things together because, we're impacting groundwater, but we also rely on it for water supply. And these issues are only becoming more prevalent over time. So that's kind of what got me interested in it. And then the switch to engineering, I just found it kind of provided a little bit more opportunity on the, to take the problem solving to the next level and do more of the design work and, just a little bit more flexibility than the geological sciences route. So I switched after my second year at UBC.
Awesome. Thanks for sharing. It's always tough, right? Choosing your degree, especially coming from high school. I'm sure a lot of the people in the audience can relate to that. So thanks for sharing.
All right. So yeah, about my research. So after my undergrad degree in geological engineering, I started working in industry. And I'd been working on some of these large projects, especially mining projects that really collect a lot of groundwater data. These are big, complicated projects and they're interacting, with the environment. You can see here the mine up on the plateau. There's this facility here full of tailings and water with heavy metals. And then downstream of that, you have lakes, communities downstream. And so, there's a lot of complex issues here around contamination and also water supply. There's pumping water for drinking and also for mine use. And so these sites really do collect a lot of data and, we're kind of struggling with it in industry, what to do compared to other disciplines. Like, even though I say these projects have a lot of data, other fields of engineering and science would laugh at us because it's a pitifully small data set compared to like software or something like that, right? Collecting data from the subsurface is really expensive. You have to drill for it. And so you only get a few points here and there. So this is kind of an interesting area of research where, it's machine learning, but it's going to be quite different from maybe what you are used to seeing. So this is the mining project that kind of inspired my research. So I created this project and went back to UBC to see what we can do with some of this data. So here's that same mine map and just showing locations where we do have different types of data. And so for my research, I'm focusing on what's called like piezometer data. And it's basically at these locations with green dots. There's sensors installed below ground and they're measuring groundwater pressures. And so you can see that there's kind of a concentration of those sensors here. This is a big dam. It's like 100 meters high. And so monitoring groundwater pressure is really important for stability and also for groundwater flow for, studying contamination and issues and things like that. So at each of these points, you end up with a time series. We collect measurements every few hours. And so, this is starting to get to be quite a large volume of data, and it really contains a lot of information, but it's kind of difficult to interpret. So this pressure information, I won't go into this too much, but essentially it's a measure of energy, and it tells us how groundwater flows. So groundwater wants to flow from a location with high energy, so high, we call it head. And if you have a higher head elevation and a lower head elevation, groundwater will flow from high to low. That's the gist of what the data we're working with. So it's really these time series data that we want to use machine learning to help us look for patterns and kind of turn this mess into something meaningful. So the gist of what I did with my research, I input these time series and I run this machine learning analysis. It's called the self-organizing map. And out of it, I get this map here with a smaller number of patterns. So here I have about 80 something input time series, and I choose how many patterns I want to get out of the analysis. So in this case, I've said 10, and these output patterns kind of represent a group of the data. So this one, for example, is, represents about 3 of the inputs. And then this is called a self-organized map because the analysis will also order the patterns, placing similar patterns close together. So these patterns are more similar and different patterns further apart. So you can see this one's obviously very different from this one. So that's the gist of what we're doing. And I won't get into the method too much, but the thing with machine learning analysis, usually we specify a few kind of parameters to guide the training, but then a lot of the analysis, like how it picks out the patterns, it's unsupervised. The algorithm does it automatically, and how it does that is it kind of steps through each of the input data. So at one step, you look at one piece of data, you compare it to the map patterns, and essentially the algorithm will just update the weights and shift patterns and reorganize the map until kind of it achieves what it thinks are some meaningful patterns in the data. And you loop through the data a bunch of times. So that's kind of the background of what the analysis is doing. And so, these are what we get out. Again, we could choose how many patterns to spit out. And this really allows us to explore the data in new ways. So, this one especially, rather than having to look through like hundreds of time series and try to understand how similar they are, now we have a smaller number of patterns. And we can look for groups. So in this case, like I've picked out these groups with similar behavior. So this is a part of the subsurface that's not really responding very much to pumping. There's basically nothing happening here, whereas there's, these are behaving differently. And so I think people often are used to thinking of machine learning as kind of replacing the work that we do. It can kind of does a lot of stuff behind the scenes, but in our discipline, because we still have, a lot of missing data and we have to do a lot of interpretation, like this is actually where the work begins. So it's great that, machine learning has made this easier for us, but we still have to look at this output now and try to figure out, okay, what's the significance of, say, this group, and how does that relate to kind of our engineering goals? And, looking at different sizes of different outputs too can really help see the data in a different way. So looking at few patterns, it makes it easier to interpret. But say you really wanted to focus in on, this area, it might be helpful to go to a higher level of detail now and really see more variability. So there's a lot of, flexibility with this type of an approach. And then really kind of the ultimate goal is to bring it back to the real world. So we start to look at things in 3D space. So this is just a plot of, I mentioned those sensors in the subsurface. So this is a plot showing where they're all located. This is approximate ground surface. And then, we can color them according to their groups. And so, looking at these patterns, especially, then we can start to see the different trends over time. And, this is just one good example where this zone kind of in the middle of the valley, it's sort of increasing over time and it's not very well drained. And so that's actually a very significant finding in terms of engineering, because remember, we've got a giant dam on top of these piezometers. And so, that's the type of trend that you would want to account for in your design. So that's the gist of what we're trying to do here with machine learning pattern recognition. This application is pretty different from probably what you're used to seeing or hearing about. And And, that was the summary of my research. So the outro question that Franco wanted to ask.
Yes, that's all incredible stuff. So thank you, Emily, for sharing that. And of course, to wrap up your research, your presentation today, if you can share a little bit with the audience here, what is next for you?
Yeah, so I'm going back out into the working world, and I'm looking for, new interesting groundwater problems, and, kind of the typical, like I work in consulting, so we work on a lot of different projects, but the general workflow is like we go out and we collect data. So, we install new wells and sample groundwater, and then we do analysis, predictive modeling, that sort of thing. And ultimately, say it's a contamination issue, we would usually are designing solutions, to try to capture and mitigate contamination. So yeah, that's kind of it. Just looking forward to putting into practice what I've learned in my research. Like, again, we've got lots of data here in industry, so.
Amazing. Well, again, thank you so much. Everyone, give your thanks to Emily for sharing it in the chat. So thank you for sharing your research with us today. Amazing. Okay, so next up, now I would like to introduce our next speaker, Dr. Dylan Goode. All right. Oh, hey, Dylan. How are you?
Hello. How are you?
Good. Thanks for joining us here today. So Dr. Dylan Goode has a PhD in mechanical engineering obtained at UBC's Okanagan campus. Dylan was born and raised in Langley, BC, and graduated secondary school in 2011. After working for 2 years, he spent the next 11 years achieving his bachelor's, master's, and PhD degrees at UBC's Okanagan campus. So today, Dr. Goode will be speaking about a new approach to prosthetic heart valves in his presentation today. So to get us started, Dr. Goode, can you, before you dive into your research, can you tell us a little bit about your path into graduate studies?
Yes, actually, I didn't really know what I wanted to do in my last year of my undergrad, and I thought I would go into renewable energy because that was where I had interest, but I wasn't sure how to apply that knowledge. It wasn't until I took a biomedical engineering course, and it was the first time I was engaged in every single lecture. Everything seemed interesting to me, different topics of how we could apply mechanical knowledge towards a biological problem. And I never took bio in high school or anything like that, but I realized I can use what I've learned during my engineering degree to be able to apply to a biological problem. So that's when I asked the professor, Dr. Mohammadi, if he would want me to take on a master's project, and I've stuck around since then.
That's awesome. Just the thing that you never even thought about going into this space, and that's kind of what the university degree is all about, right? Being open to new experiences and just taking advantage of them. So that's incredible. So over to you for a little bit more about your research.
Sounds good. As you said, my name is Dylan Goode. I got all my degrees at UBC's Okanagan campus, and my area of research is around prosthetic heart valves, and more specifically, heart valve design. And my research highlight is titled A New Approach to Prosthetic Heart Valves. Quick background around the heart. The heart has 4 chambers, that being the left and right atrium and the left and right ventricle. This is a section view of the heart, so it's as if we're looking through the person's chest. So the left side of the heart is on the right side of this image. Between those chambers, we have the 4 valves in our heart, which include the tricuspid valve and the pulmonary valve on the right side of the heart. And then we have the bicuspid, also known as the mitral valve, and the aortic valve, which is kind of hidden by the pulmonary valve here on the left side of the heart. Here is a bit of a visualization of how blood flows through in and out of the heart and through the valves. There are different reasons for a patient to need a new heart valve due to diet, age, genetic abnormalities, and so on. In addition, the valves on the left side of the heart are more prone to issues as they face more stress as the heart pumps blood to the rest of the body, while the right side of the heart pumps blood to your lungs. You'll notice that the left ventricle and the aortic valve are highlighted in this slide, and that's because it's the area of focus for my research. In terms of full valve replacement, surgical valves can be broken down into tissue valves that use pig or cow tissue to replicate the native valve, or mechanical heart valves that use a carbon-based material to form the valve. Both have their own pros and cons, as tissue valves have great hemodynamics as they replicate that native valve, but longevity is the issue as the valve will start to deteriorate over 10 to 20 years, requiring the patient to need another surgery. For mechanical heart valves, they last the lifespan of the patient and won't require additional surgeries, but the patient is required to be on anticoagulation therapy or blood thinning for the rest of their lives due to the valve having subpar hemodynamics. With this said, there's no one valve that can provide the best of both worlds and achieve that holy grail. That leads us to my work. Here is the I valve, bileaflet mechanical heart valve, which gets its name by the similarities to an eyelid blinking. This valve has been developed at the Heart Valve Performance Laboratory at UBC's Okanagan campus and is the only mechanical heart valve out there that can offer one orifice, which greatly improves hemodynamic performance, in addition to several other design components that help it stand out. All prototypes have been fabricated by myself on our tabletop 5-axis CNC in our lab, which allowed us to make our most recent prototypes out of aluminum and PEEK to be able to test. We're able to take our prototypes and test them in a heart simulator that provides similar conditions to our heart while providing important data for analysis. The valves were placed into the aortic position for the evaluation on the heart simulator. With the prototypes in place, we can evaluate what kind of pressure is dropped as flow goes through the valve. The flow rate through the valve and the area exposed to flow using a light diode and a light source and a photodiode. We compared the I valve to the industry standard mechanical heart valves along with a tissue valve. I know this is a lot of data, so I'll try to point out the important parts. The I valve on the left had similar opening performance to that of the mechanical heart valves, seen here by the consistent open area, which is optimal to allow the most amount of blood flow through the valve, but it had a closing performance that was more close to the tissue valve rather than the larger spikes that were seen in the mechanical heart valves, which are a major contributor to why those valves need blood thinning. Based on this data, we can hypothesize that the I valve has hemodynamic performance that is closer to the tissue valves rather than the mechanical heart valve counterparts. We believe the I valve can provide the best of both worlds when it comes to heart valve replacement, with the goal of having a valve that can last the lifetime of the patient without needing blood thinning. Plenty more validation to go for this valve, but based on my work, the I valve could be the prosthetic valve of the future. That concludes my presentation. Thank you all for listening, and there might be another question coming up.
Yes, amazing. Thank you for sharing your incredible research here. So Dr. Goode, to wrap up your presentation today, can you please tell us a little bit about how engineering and your research has changed your view of the world?
I think the biggest thing I can take away is I have an appreciation for all the hard work put into everything we live in our day-to-day lives. In my area of research, I know the amount of clinical trials, preclinical trials, and all the steps that these medical devices have to go through before they get to be able to be put into a patient commercially. So I have an appreciation for when I look around of, say, an airplane and how many hours, thousands and thousands of hours have been put in to making sure that it's safe for us to use. So that's my appreciation for engineering. I really just can look at things and really take it in and understand that there's a lot of hard work behind that.
Awesome. Thank you so much. And thank you for taking some time to chat with our students here. Appreciate your time.
Awesome.
All right. And now, last but not least, I'd like to introduce Dr. Cao here to the stage. Hello, Dr. Cao. Thanks for joining us here. Dr. Cao is an associate professor in the Department of Chemical and Biological Engineering. Now, his research focuses on the design and implementation of large-scale optimization algorithms. So his group are using these algorithms to address engineering and scientific questions that arise in diverse domains. So that would include optimal decision trees, optimal clustering, machine learning, base control, optimal power system planning, estimation of battery health, and process monitoring for bioreactors. Dr. Cao's presentation today will be focused on AI-enabled process systems engineering. So Dr. Cao, thanks again for joining us here. Before we dive into your research, can you tell us a little bit about your lab and how undergraduate students can get involved?
Sure, yeah. Thank you very much for the question. So for my lab, we mainly focus on computational works. So although we are in chemical engineering departments, we work on computational works. We don't do lab works. So mainly we develop computational tools so that we can design those energy systems to be more sustainable, or to control these systems to be more sustainable. So every year we have lots of undergrad students working in our group. Typically, they join our group in the summer, like when they don't have courses. We have undergrad volunteers. Typically, it's like third year or fourth year students. But sometimes during the winter seasons in our department, we have a course called undergrad thesis course. And typically, it's the last year undergrad students, they can take this course. It's a 2-semester course. I remember it's probably like 6 credit or something like that. So students can take this course and do research with a supervisor, typically like a faculty in our department. Yeah.
Awesome, thanks for sharing. So for any of our prospective students who might be interested in doing research in their undergrad degree, Dr. Cao here has confirmed that there are opportunities for undergraduate students. So over to you for your research.
Okay, thank you very much. Thank you very much for the introduction. I'm glad to be here to present our research on developing some computational tools for sustainable energy systems. So I'd like to first give an overview of the work in my group. So my group works on the design and some implementation of some computational tools such as AI algorithms, optimization algorithms, and control systems. So we use those high-performance computing hardwares like HPCs or GPUs to run our codes, and we also apply those tools that we developed to solve problems from various applications, especially focusing on sustainable energy systems. For example, here we work with BC Hydro in order to manage their water resources more efficiently and produce more electricity from their systems. And we also work with lots of other companies in order to optimize their process and also reduce their energy consumptions. So here's one application that we focus on. We all know that Canada, especially British Columbia, we have lots of forest resources. And at the same time, we also have lots of forest residues or waste from these resources. So a substantial amount of this biomass residues or waste is traditionally burned in the open air. So it is not only a significant economic waste, but also it contributes to air pollutions and also wildfires. We can actually convert this biomass to produce very valuable bioproducts such as biochars. It can be used as energy or used as fertilizers. But typically this conversion is carried out in large centralized facilities. But the transportation cost of moving these raw materials can be very, very high because those raw materials typically very loose, wet, and bulky. So it's quite expensive to move those raw materials from the forest to those large facilities. So to overcome this challenge, we have a postdoc. His name is Kevin. In my group, he co-founded a startup company. The startup company is called TACCHAR, and they developed a new small-scale reactors. So this company has won lots of awards worth millions of dollars, and their small-scale reactor, which is something like here, and this reactor is very small so that we can move those reactor with a truck to the forest. And in this way, we can process those biomass directly in the forest or in the field. And the benefits here is that we only need to transport the products. And you can see the product is way smaller than the raw materials. And in this way, the transportation cost can be significantly reduced. So here, I'd like to highlight 2 technical challenges that my group are addressing on operating the bioreactor. So one challenge here is that for this bioreactor, under normal conditions, it will go through some reaction and it will produce biochar, and this is the products that we would like to have. However, under undesired conditions, and it's very rare, but it happens that it can produce ash and smoke instead. And it's not only a big waste of biomass, but also raise some environmental concerns. So the difficulty here is in the real-time detection of the smoke, because the operator of this reactor may be quite busy, occupied with various tasks, and might not quickly notice this smoke. So what we do is we actually add a camera to provide some video monitoring of this bioreactor process, and then we develop some computer vision techniques. It's called a transformer, and it's basically a variation of neural network to quickly identify the smoke from the video monitoring, and it will alarm the operator when smoke is detected. So once it is detected, this unexpected issue can typically be resolved very quickly by making some adjustment to the feedstock. So another challenge here is the classification of those wood biomass. So the process conditions, the optimal ways to control this process can be quite different for different types of wood biomass. And the operator requires lots of training to correctly classify those wood biomass. And the difference between different types of materials can be quite subtle. So what we do is, again, we develop some computer vision techniques based on deep neural networks and also something called self-attention mechanisms to automatically and precisely classify those wood images. And the classification accuracy can be quite high. So that's all I have today. Thank you very much.
Amazing. Yeah. Thank you, Dr. Cao, for sharing that. And as we look to wrap up today, I have one final question for you. So can you share with us how your research informs your teaching?
Oh yeah, so it's a very good question. So for me, like I teach 3 courses. One is undergrad control course, one is graduate control course, and one is an optimization course that's open to both undergrads and control and grad students. So from research, I learned lots of sustainable energy systems, and typically I would put some into the homeworks or projects or even exams for students, and it helps them to learn about the application of their computational tools. For example, for one of the projects, I asked students saying, this is one of the sustainable energy systems, and here is the mathematical equations, and you can please propose a new design or a new control system for this system so that the process is more sustainable, something like that. So it helps us to help students to learn. Yeah.
Amazing. Maybe Dr. Cao could be your professor if you decide to join us here at UBC. Yeah. So awesome. Thank you, everyone. I want to say a huge thank you to all of our researchers here who took some time out of the day to share their research with all of you. This recording will be available for you to watch if you weren't able to watch to catch the entire session. We're going to wrap up the stage right now, but we will be back in just a few minutes to start our next session, which is our why engineering presentation. Thank you, everyone, and we'll see you soon.